Welcome to another trainML tutorial. trainML is a GPU as a service platform specifically designed for deep learning. Our platform lets you get up and running on GPUs with just a few clicks without the need for managing servers, learning a new framework, or enduring a lengthy software implementation. In this tutorial, we will walk through how to get started training models using notebooks. We will create a notebook that uses PyTorch to train an image classification model on the ImageNet dataset. Once we're familiar with that, we'll move on to using notebooks to run training experiments on the same model in parallel. To create our first notebook, we can click Start a Notebook from the trainML platform dashboard. This will launch the job form that allows us to specify the resources our notebook requires, as well as allows us to pre-populate the notebook with data, model code, or software packages and libraries. We will enter PyTorch image classifier as the job name and select RTX 3090 as the GPU type. We can also configure the notebook to have multiple GPUs, or increase the size of the notebook's working directory space quota if desired, but we will leave these as the default for now. If we expand the data section, we have the opportunity to add one or more datasets to the job. Since we want to train our classifier on the ImageNet dataset, we will add it from the public datasets list. Public datasets like ImageNet are provided by trainML at no cost. As you can see, the dataset is over 150 gigabytes, but our notebook's disk size is only 10 gigabytes. When you're using the trainML provider, the dataset storage is independent of the job, so you can reuse the same dataset over and over without paying additional storage costs. Since this is a public dataset, you don't pay any storage costs at all to use it. We also want to preload the model code we have stored in a Git repo, so expand the model section to specify this. Keep the model type as Git and specify the trainML examples repository in the model code location. In the environment section, we could choose a different pre-built base environment, add any pip or app packages to be installed during the job provisioning process, or add environment variables and third-party keys if necessary. Our model doesn't need any of these right now, so we'll just click Next. The job review form shows us what we selected on the previous screen. It also indicates the directories inside the notebook environment itself that the data and model code will be loaded. Click Create to start the notebook. When notebooks are first created, they download the model code, cache the dataset to the local storage of the GPU-enabled system, and build a dedicated and permanent environment for the notebook that will remain as long as the notebook exists. You don't have to reinstall libraries or re-download files or other dependencies every time you restart the notebook. Once it's ready, click Open to access the Jupyter Lab environment. Notebooks are a great way to get familiar with the job environment that is common to all trainML jobs. On the left side, you can see the input folder that contains the ImageNet dataset we selected. The Models folder contains the code repository we requested in the job form. If you open a terminal window, you can also see the same files and where they are relative to the root directory. You can view any environment variables that are configured, or check the status of the attached GPU with the NVIDIA SMI command. The example notebook is in the Notebooks folder of the Models folder, which we can open by double-clicking. The code is organized in a way to keep the available hyperparameters that we might want to change near the top so they can be easily accessed. The rest of the code is largely based on the ImageNet training example provided in the PyTorch examples repository. One thing to note is the data loaders section. This is an example of how you can use trainML environment variables to let your model know where the data, model, or output is stored without having to memorize the directory paths themselves. If we scroll back up to the hyperparameters section, you can see some initial values we selected for the learning rate, model architecture, momentum, weight decay, etc. For this example, we're going to lower the number of epochs to 2 so we can get a sense of how the training is going without spending a lot of time on it up front. To start the training with these values, go to the Jupyter menu and click Run All Cells. Scroll back down to the training loop section, and we can start to see progress from the batches come in. Depending on what GPU type you selected and how many epochs you've configured, the training process could then take anywhere from 15 minutes to several hours. Now that we know the model's training loop is working, we might want to try a few more sets of hyperparameters to make sure we're training the best model we can. However, if the model takes several hours per try, we'll be taking a lot of coffee breaks between trials if we have to wait for each one to finish before starting the next one. This is where notebook forking can come in handy. If we go back to the notebook dashboard and select the notebook that's currently running my model training, we can click the copy button to see several different copy types. The full copy type will take a snapshot of the current notebook's job environment and working directory and automatically create a notebook from that snapshot. Any installed packages, temporary files, etc. that exist in the source notebook will be copied, so the notebook begins as an exact duplicate. You can give it a new name and even change what GPU type the new notebook will use once it's copied. Once the copy is complete, the new notebook is now independent of the original notebook, and changes in either will not affect each other. The new notebook will automatically start once the copy process is complete. We can now open the new notebook instance, reopen the notebook file itself, and change the model architecture in the hyperparameters section. In this case, we'll try the VGG16 model. Since this model is substantially larger than our original ResNet 18 model, I know that we'll have to lower the batch size as well in order to avoid CUDA out-of-memory errors, so we'll set that to 256 as well. Now we can run all cells again and scroll down and watch the training loop output. Note that if we go back to the original notebook, the training process continued while the notebook was being copied. We can repeat this process as many times as we'd like to run as many different notebook experiments in parallel as we need. Once the training processes for each of the notebooks completes, you can compare the final accuracy numbers and download the model checkpoint files as needed. Once you're done with the notebooks, be sure to stop them to end compute billing. Once they're no longer needed, terminate them to end storage building. As we've seen in this tutorial, trainML notebooks make it easy to start training models on GPUs. The ability to copy notebooks in their entire execution environment allows you to run parallel training experiments on demand with just a few clicks. If you'd like to learn more, you can check out our documentation site at docs.trainml.ai or shoot us an email at sales@trainml.ai. If you run into challenges running this example or anything else, you can always contact us at support@trainml.ai. Thanks for watching.